Good morning, afternoon, or evening, cats and dogs. Today's video comes from the lesson 12.3 guided notes on area of composite figures. We're actually going to start with some other formulas first, and then we'll eventually get into, after we practice finding area of just simple figures, we'll find the area of composite figures, which are seen really frequently in real life. Now, you do have a formula sheet that has these formulas on there, so you may want to have that handy as well. It should be on yellow paper that's like a thicker paper, but they're also in these lesson 12.3 guided notes. So let's talk first about some area formulas. We already talked about the area of a rectangle. It's length times width or base times height. Keep in mind this is an L right here, not a 1. I know it looks a lot like the number 1, but that is in fact an L. We also have the area formula for a square, specifically for a square, is S squared. S representing the length of one side. Now you might have to fill that in your guided notes. Can't remember if I typed it in there or not for you, but S to the second power will represent the area of a square. For a parallelogram, we're going to use base times height. Now this is different from length times width because your length and width automatically intersect at a 90-degree angle in a rectangle, whereas in a parallelogram, all of our angles aren't 90 degrees, although technically a rectangle is a type of parallelogram. So we do say base times height here because what's going to be really important for us is that our base and height intersect at a 90-degree angle. So you're looking for a 90-degree angle for your height and your base to intersect. The base does not have to be the bottom. A lot of times it is, but it doesn't have to be the bottom of the figure. It's where your height intersects at a 90-degree angle. And I think that's also pointed out maybe on the top of the next page as well. For a triangle, it's half times base times height. You can also do base times height divided by 2 or times 0.5. That also works. But again, your base and height are always going to intersect at a 90-degree angle. Then for a trapezoid, it's important to know what a trapezoid is. A trapezoid has one pair of parallel sides. Your other pair of sides will not be parallel to one another. So your formula is A equals half times the height. Then in parentheses, B sub, like a submarine, B sub 1 plus B sub 2. B sub 1 and B sub 2 are the lengths of the parallel sides. That's going to be really important. It's our two bases, and our height will intersect those bases at a 90-degree angle. But again, H is your height. B sub 1 and B sub 2 are the lengths of the parallel sides. Now, I know I already stressed this, but I'm going to stress it again. The base B and the height H will always touch each other at a right angle. It helps you identify both the base and the height. And then the bases of a trapezoid. In case you don't remember, a trapezoid is a four-sided shape that has one pair of sides that are parallel to each other. Those two sides that are parallel are called the upper base, B sub 1, and the lower base, B sub 2. Again, those are going to be the lengths of the parallel sides. I want to stress here that the little numbers that are down below those B's are not exponents, and it's not multiplication. It's just a way of numbering our two bases as base 1 and base 2, since we have two of those, a pair of parallel sides. All right, let's get into our examples of finding the area of some simple figures, and then we'll eventually work our way into composite figures. So number 1, let's go ahead and start with this question. This is a triangle. We want to identify the shape first so we know which formula to use. So the formula for the area of a triangle is half times base times height. So first thing I'm going to do is jot down the formula, and I apologize the quality of this work isn't as good since I copied it from an answer key that I had. Now I have to identify the base and height. They're going to intersect at a 90-degree angle. I see a 90-degree angle here, so that tells me that my height is going to be 2 and my base is going to be 3. It also tells me then, we're going to give you some extra numbers you won't need to use, that I do not need the 2.5 centimeters. So you can cross it out since we won't need it here. Perimeter we would, but we don't need it for the area. So half times base times height would be half times 3 times 2. If you put half times 2 times 3, that's fine as well. You should be able to calculate that without a calculator. Half of 2 is 1. 1 times 3 is 3. You can also do 3 times 2 to get 6 and then do half of 6. You don't need to show this third line down. I would always start by writing your formula, plugging in the numbers, and then evaluating it, which means calculating it. We get 3 centimeters squared. Note the label on this. It should be centimeters squared or square centimeters since it's area. It's the amount of space inside the figure. All right, number 2, let's identify this shape as our first step. This is a parallelogram. So the formula we're going to use is base times height. So the base and height are going to intersect at a 90-degree angle, which I see right here. So that tells me that my height is 2.5, and my base would be this side down here, but opposite sides of a parallelogram are congruent, so 3 meters could also be our base, since this is also 3 meters. So we do not need the 4.2 here, since it's neither the base nor height of the parallelogram. So we can do 3 times 2.5. That will get us an area of 7.5 meters squared. Don't forget your labels. Your labels are definitely important. All right, taking a look at number 3. This is a trapezoid. So the formula for the area of a trapezoid is half times the height, and then in parentheses, b sub 1 plus b sub 2. So I'm going to identify my right angle, which is here, and my parallel sides are going to be my 2 bases. So that's going to be this side, which is 7 millimeters, and this side, which is 26 millimeters. The height is going to be the distance between those 2 parallel sides, which is my not straight line, but 17 millimeters. I do not need the 22 millimeters or the 18 millimeters. Those are my non-parallel sides. If I said find the perimeter of this trapezoid, you would need those, but I don't need it for the purposes of area. So let's plug in the numbers. That's half times 17, and then in parentheses, 26 plus 7. It doesn't matter if you have 7 plus 26, but 26 and 7 need to be added inside the parentheses. 26 plus 7 is 33, so we have half times 17 times 33, and that's half of 561. Again, you can skip this second to last step if you don't need it and just plug half times 17 times 33 into your calculator. That will get us 280.5 or 280.5 millimeters squared. Okay, so let's continue with numbers 4 through 6. So in number 4, we want to identify this shape. It is also a trapezoid, so our formula will be half times the height, and then in parentheses, b sub 1 plus b sub 2. So we want to identify our bases, which are going to be our parallel sides. So that is going to be the 19 feet and the 7 feet. Our height will intersect at a 90-degree angle, which I can see right here. So that's going to be 7.5 feet. It means that I do not need the 10 feet or the 8 feet. Those are the lengths of the non-parallel sides. So I'll plug in what I know. It's basically just plug and chug once you identify what you need. Just please make sure you're plugging these into the calculator to make sure you know how to plug it in, that you're not making any careless mistakes. So we've got half times the height, which is 7.5, and then in parentheses, 19 plus 7. Remember, the 7 and the 19 can be in a different order, but the 7.5 has to be your height. You can't move that into the parentheses. So we'll do half times 7.5 times 19 plus 7. I do like to do that 19 plus 7 first before I plug it all into my calculator. It's really important that the 19 plus 7 is in parentheses. If it's not, your calculator is going to multiply by 19 and then just add 7 onto that answer. So I would just do 19 plus 7. And then plug half times 7.5 times 26 into my calculator. Again, this second to last step you don't need, but you should get 97.5 or 97.5 feet squared or square feet. All right, let's go ahead and take a look at number 5. So this is a parallelogram since both pairs of opposite sides are parallel. Our base and height are going to intersect at a 90-degree angle, and I see that 90-degree angle here. So my height is going to be this 9 yards. My base will be the 4.5 yards, and both the top and bottom are 4.5. The formula for the area of a parallelogram is base times height. We just need to take 9 times 4.5. You do not need the 10 yards since it's not the base or height of this parallelogram. So 4.5 times 9 will get us an area of 40.5 yards squared. Now before we move on to number 6, I want to look at this question that's down below here. Let me delete this box or get it out of the way. It says Giles's backyard is shaped like the parallelogram in number 5. That's the question we just saw. He would like to put new sod or grass in his yard. If it costs $12.50 per square yard, how much will it cost to sod his yard? So if he wants to put new grass in his yard. We know the area is 40.5 yards squared. We know that it's $12.50 per square yard. So in order to find my solution here, I just need to take 40.5 times 12.5, or $12.50. Take your area times the cost per square yard. That will get us $506.25. It's a pretty standard question, just taking that area and applying it to a word problem. And this is something that people who come in to do renovations in your home would need to do in order to give you an estimate for the cost for work they're going to do. It might be perimeter, it might be area, it could be volume, just depending on what we're looking at as well. Or surface area would be another good example. All right, let's take a look at number 6. So number 6 is a trapezoid. It's just kind of a funky looking trapezoid. So one of the first things I would do, I'm going to move this record bar out of the way, is look for my pair of parallel sides. So in this case, that's going to be this side and this side. I'm highlighting them in yellow, not making my lines very straight, of course, but we've got our pair of parallel sides. So 7 inches and 13 inches will be my two bases. And then my height will be this 2.5 inches. I do not need the 5 inches or the 3 inches. Those are the non-parallel sides. So I put this question in here because students often have the misconception that the top and bottom have to be your bases. And that's just not true. We can switch the orientation of the trapezoid around so that the parallel sides are not the top and bottom, like is the case in number 6. So it's just going to be really important for us moving forward. We're going to kick this up a notch from problems you might have seen in previous years. So we're going to do half times the height, which is 2.5, and then in parentheses, 13 plus 7. Again, before I calculate this, I would do 13 plus 7 to get 20. I do half times 2.5 times 20, and that ends up getting us a solution of 25 inches squared. Let me try to get this box out of the way for us. So our area of this trapezoid is 25 square inches. All right, let's continue with our last 3 somewhat standard simple figures: trapezoids, triangles, parallelograms, and so forth. So in number 7, the first thing we want to do is identify what shape this is. We have one pair of parallel sides, so this is going to be a trapezoid. So our formula is half times the height, and then in parentheses, b sub 1 plus b sub 2. So let's identify our parallel sides. That's going to be my left and my right-hand side of this shape. Our height needs to intersect at a 90 degree angle. I just made that worse when I created my line there. But our height needs to intersect at a 90 degree angle. I can see that 90 degree angle down here. So that means our 6 meters is going to be our height. And I know that seems kind of weird because it's going left to right. It's a horizontal line. But you can also think of it as the distance between your two parallel lines. I do not need the 6.5 as part of this. It's one of the non-parallel sides. Now, one of our sides happens to be our height, which is unusual. We haven't seen that up to this point. But that's why I threw this question in here. So b sub 1 and b sub 2 are your parallel sides, 8.5 and 7.5. 6 is your height. It intersects our bases at a 90 degree angle. So we're going to do half times 6, and then in parentheses 8.5 plus 7.5. That's going to get us half times 6 times 16, and our final area will be 48 meters squared, not 45, so 48 meters squared. All right, again, you're noticing you probably have seen some of this before, but we're adding extra numbers you don't need in the problem. We're changing the orientation of what the triangles or the parallelograms or the trapezoids are in, so it makes it a little bit more challenging. So let's look at number 8. This has both pairs of opposite sides being parallel. So this is a parallelogram, which tells me I'm going to use base times height. Our base and height are going to intersect at a 90 degree angle, which I can see right here. So my height is 1.5, my base will be 3.5, and it means that I do not need to use the 3 since it is not the base or height of this parallelogram. So we'll do 3.5 times 1.5. That's going to get us an area of 5.25 centimeters squared. Taking a look at number 9, this is a triangle. So our formula is half times base times height. So let's identify our base and height. We've got a 90-degree angle here. Pulled my box down a little bit too far. I might have given it away. My base is going to be 13 meters since our base and height intersect at a 90-degree angle. My height is 3, and that means I do not need to use the 5.5. It just happens to be one of the sides of the triangle, but not the base or height. So we'll do half times 13 times 3. The area of this triangle is going to be 19.5 meters squared. Some quick reminders for how to approach these problems. First thing, identify the shape. That will tell you which formula to use. You don't have to memorize them. You can use your formula sheet. Write down the formula, identify what parts of the formula you need and what parts of the figure you need. Cross off any extra numbers that you don't need. Remember that the base and height have to intersect at a 90-degree angle. Plug them in and basically just chug into your calculator and go with it to get your solution. The last thing you want to make sure you do if you're finding area, put a label of meters squared, inches squared, feet squared, centimeters squared, etc. on your solution. You will lose points if you don't have a label or if your label is incorrect. Think about if you are working in construction and you're not putting labels on your dimensions. If we don't know whether something is inches or whether it's feet, we're going to have a real problem with those measurements. We need to know what they are and what they represent. So question number 10 is where we start to mix in scale with our area questions. With scale drawings or scale models, I want to remind you that the scale is the ratio of the measurements in the drawing or model to the measurements of the actual real-life object. If a map scale is 2 centimeters equals 5 miles, then every 2 centimeter on the map represents 5 miles in real life. And we often have scale models and drawings when we're doing construction or coming up with plans to build a house or renovate a building or build a bridge or so forth. So looking at number 10, we want to find the area of this trapezoid in square kilometers. I suggest converting the measurements from meters to kilometers first, and then you don't have to worry about doing that at the end, finding the area after you convert those measurements. But I'll show you how to do this by converting afterwards. We did talk about this with a PSSA item sampler question previously, so you might have seen something similar to this before. So the first thing I did was I took all of my measurements, I converted them from meters to kilometers. And the way that I did this, since the scale is that 1 meter equals 5 kilometers, is I just multiplied each of these numbers on the left by 5. 1.6 times 5 gets us 8 kilometers, so the 1.6 meters is equivalent to 8 kilometers. 1.8 I took times 5 to get 9 kilometers for this side. 4 meters times 5 got me 20 kilometers. And then 2 meters times 5 got me 10 kilometers. Now, I want to point out that since this is a trapezoid and we're doing half times the height, and then in parentheses b sub 1 plus b sub 2, our parallel sides are our two bases. So that's going to be these two sides right here. Our height is going to be this 1.6 meters. I do not need the 1.8 meters or the 2 meters, and you can actually just kind of cross them out here if you want. I did find all of them just to convert each of those measurements. But what you might want to do is just kind of put next to this, the 1.6 meters is equal to 8 kilometers. Make that a little bit smaller there. There we go. And this, I'm just going to go ahead and copy and paste that. This side right here is also 8 kilometers, our height. And then our 4 meters is equivalent to 20 kilometers. It's not a bad idea. You can even cross them out and write them next to it if you want. So I'm going to do half times the height, which is 8 kilometers. And then in parentheses, my two bases are my two parallel sides. Those are 20 and 8. So I have 20 plus 8 in parentheses. So that will be half times 8 times 28. And that will get us an area of 112 kilometers squared. Again, since my measurements that I plugged into the formula were in kilometers, my answer is in kilometers squared, which is what it asks us for. So we can convert after. We can use the 4, the 1.6, and the 1.6, which I'll show you here off to the right. So we can use our formula. You can see how clear this is. This is something I added in just brand new, so it's a little bit more clear than the stuff on the left. But we can do half times the height, which is 1.6. Let me slide this up. And then in parentheses, 1.6 plus 4, which are our two parallel sides. That'll get us half times 1.6 times 5.6. That gets us an area of 4.48 meters squared, but we need our answer in kilometers squared. So you have to recognize that 1 square meter doesn't equal 5 square kilometers. You need to square each of those numbers. So 1 square meter is actually 25 square kilometers. A lot of times students want to just multiply this by 5, but you notice if I take 4.48 times 5, it's not going to get me 112. But if I take 4.48 times 25, which is how many square kilometers I have in a square meter, that will give me the same answer of 112 kilometers squared. I don't suggest this method on the right because students, one, don't usually convert meters squared into kilometers squared correctly. The other thing is they get to the end and say, oh, I'm done, I've got my answer 4.48, and they forget to multiply by something at the end. So I do suggest convert them first, get it out of the way, and then just plug and chug in your formula, and it makes your work just a little bit simpler. So we're going to continue our exploration of area questions by looking at composite figures. So I first wanted to start by showing you some real-life examples of composite figures. For example, porches and decks pretty frequently are going to be composite figures. They're made up of more than one simple shape, and we'll talk about that definition in a moment. We might have a pole, for example, that's not necessarily shaped as a rectangle or shaped as a square or shaped as a perfect circle. It might be several circles put together plus some other shapes. When we look at the layout of a house, for example, it's often made up of a lot of different rectangles, possibly trapezoids like in this example up here towards the top. But we often have several shapes put together to make one larger shape. So that's what we deal with when we see composite figures. By definition, composite figures are shapes that are made up of more than one simple shape. So again, maybe a rectangle with a semicircle, or a rectangle and a trapezoid, or a square and a triangle, for example. A lot of shapes in real life are composed of more than one simple shape, so that's why we talk about these composite figures. To find the area of a composite shape, first separate the shape into figures that you know and you know how to find the area of. Find the area of each shape and then add these areas together. Now this is going to be a little bit different when we talk about the perimeter of composite figures, since you wouldn't separate it and then find the perimeter of each shape. But for the area, since we're looking at the space inside, separate it into shapes, and sometimes there's multiple ways to do that. And then from there, find the area of each shape and add those together. Sometimes you may have to find a missing side length in the picture that's not given. Do not guess what the side lengths are. You're going to have to use math, and we'll talk about that in some of our examples. So let's look at questions 11 and 12. So number 11 is already, I believe, in your notes split up for you. Kind of looks like a sideways ice cream cone, and it's composed of two different regions, a semicircle and a triangle. This dotted line is separating those two. So let's actually start with the semicircle. I'm just going to take all of this off of here to show us. But our semicircle, I kind of drew it as a separate piece. Like I took the picture apart and drew that semicircle. I know that the diameter of that semicircle is 9 yards. It goes from one side of the circle to the other. So that line goes from one end of the circle to the other, not from the center out. So that's the diameter of 9 yards. The radius is going to be half of that. That would be 4.5 yards. So when we find the area of the semicircle, we can call that region 1. Sometimes what I'll do is I'll actually label it with a 1. This is region 1 that we're finding the area of. You can also write it out in words. Numbers, though, makes it a little bit shorter. You can label them region A and B if you want, if that's easier to avoid numbers. But find a way to kind of separate the two figures. And let's go ahead and find the area of the semicircle before we talk about the triangle. So I'm just going to take all this away. The area of a semicircle is half pi r squared. I do usually use 0.5 instead of 1/2. It's just a little bit less to plug in the calculator. But our radius, we're going to replace that with 4.5 since that's half the distance across the circle. So we'll do half times pi times 4.5 squared. 4.5 squared is 20.25. Half of 20.25 is 10.125. So if you want your exact area of this region, you can write it as 10.125 pi. That's about 31.8 yards squared. And again, that's just for the semicircle. So that's this yellow shaded region is about 31.8 yards squared. Now our second region is going to be our triangle. So I did kind of, again, just draw this as a separate picture. I'm going to call this region 2, and you can label it that way as well. So I'll just put a 2 next to this. If you like A and B better, again, you can choose that. You can also just use words. The base of the triangle is 9 yards. That's the same as the diameter of the half circle or semicircle. The height of the triangle is the distance from the top point of the triangle down to where the diameter of the semicircle is, or where the base is, and that's 13 yards. The formula for the area of a triangle, and this is where it's really important to write those formulas, is half base times height. So we're going to do half times 9 times 13. That's going to be half of 17, and so the area of that region, which is our triangle, is going to be 58.5 yards squared exactly. So that's the area of this green shaded region that we have here. So to find our total area, and I put a line down here for us to do that, we just add all these together, add these two values together. We've got 31.8 from the semicircle plus 58.5 from the triangle is going to get us an approximate, we did have to round for the semicircle, area of 90.3 yards squared. It's important to try to round appropriately. If you round appropriately, we should all get the same answer, but if you don't, you may be a tenth or two off. All right, let's take a look at question number 12. These problems do take a while. So the way I split this up in the notes, and I apologize, you can kind of see these little dark lines here. These got misaligned, and I forgot to correct it since last year. I did since do that, but we're going to put our lines to split this up right here. You can make it a dotted line or a solid line, and right here. Again, they got misaligned when I changed some things. So I broke this up into 3 rectangles, different sized rectangles. So we're going to start with the rectangle that's at the top, and I'll move this up so you can see that work. I'm going to call this region 1 right up here. Again, if you like A, B, and C, since I split it into 3 different regions, that's fine too. But I kind of drew this this rectangle down here, and the length and width are 8 and 3, since we're looking at the entire distance across. So 8 miles wide, 3 miles high. Again, we're not using this 4 down here, because really this is still 8 miles wide, this entire length over here. So this is this yellow outlined rectangle here. Again, the dimensions are 8 by 3, so to find the area, we do 8 times 3, which is 24 miles squared. So the area of region 1, which is this yellow shaded region, is going to be 24 miles squared. And again, this is region 1. I just want to match those up for us. Let's go ahead down here. This is going to be our rectangle that's in the center. I'm going to call this region 2, so I'll label it down here as well. And we had to kind of do a little bit of math to figure out our dimensions, so I'm going to keep scrolling back and forth. I'll highlight this in green. So it's going to be these dimensions here going across, and then these dimensions here going vertically. And it's really important that you use the appropriate measurements. So this distance going across, if I know the whole way across here is 8, the whole way across here is also 8, this part right here is 4, which means this needs to be 4 as well. So this green line has to be 4 to get a total of 8 going across. So you can see I labeled that with a 4 down here. And then vertically, so I know this entire distance along here is 10. I know this yellow portion is 3, and I can label that here. So that should be 3. Down here, this height is 2. So if the total between these two, the 3 and the 2, is 5, then that leaves me with 5 for this distance, this green line right here. So you notice that I labeled that in my picture down here. So I've got 4 miles by 5 miles. And again, I'm using math. I'm not just guessing and saying, well, that looks like it's 4 or 5. I know for a fact mathematically that this is a height or a distance of 5 miles. So to find the area of that region for rectangles, it's pretty simple. It's just length times width. So take 4 times 5 to get 20. So the area of this green shaded region is going to be 20 miles squared. Let's talk about region 3, which is this skinny rectangle that we have here. And I'll go ahead and take this box out of the way here. Okay, so our skinny rectangle here, I'm going to highlight this one in blue. I just have to move this box out of the way. There we go. So the whole distance across is 6 miles. That's labeled. The height of this thing is 2 miles. So I'll just outline this whole thing in blue. So to find our area, we're going to take 6 times 2, which is 12. So the area of region 3 is going to be 12 miles squared. I'll label this with a 3. And I will shade in this region in blue. So the area of this entire region is 12 miles squared. So to find our total area, all I have to do is add my 20 to my 12 to my 24. And I would maybe circle these as you're working through or highlight them so that you can easily pick those out. Our total area will be 56 miles squared, exactly. No rounding needed here. Now it does say, is there another way to break this figure apart? I mean, there's lots of different options, and in class I normally have students come up and show us different ways to break this apart. One option would be to draw the lines vertically instead of horizontally, so you could put a line right here and another line right here, so you'd have a long rectangle along here and then some more square-like shapes over here along the right. I've had some students break some trapezoids into this, so they've actually drawn some diagonal lines and so forth. That can work as well. So you do have a lot of different options for the ways to break this up. You could do one horizontal line, one vertical line. Your in-between steps, your individual areas will be different, but your final solution should be the same. And if ever you try it a different way and you don't get the same solution, have me take a look at your work. And that's why it's really important to show the work for these, so I can figure out where you may have made your mistake if you got a different solution than we did. Continuing with numbers 13 and 14. Now, if we were doing these in class, I would definitely have you try some of these questions on your own. We're going through these questions together in the video. You can certainly try some of the questions on your own. Pause the video, try it, and then check your answers using the video recording of these solutions. So in question number 13, I kind of have what looks like a Pac-Man shape, and the way I'm going to split this up is by drawing a horizontal line to create a semicircle or a half circle, and then two triangles. The two triangles happen to be congruent, meaning they're equal to each other. So let's start with region 1, which is going to be the semicircle. So I'm going to go ahead and label this as region 1. And the area of a semicircle is going to be half pi r squared. Now I do have to identify the diameter and or the radius. I really need the radius for the formula. The diameter goes from one end of the circle to the other, and that happens to be 20 meters. That's shown down here at the bottom. So halfway would be 10 meters. So I did identify the diameter as 20 and the radius as 10. It's important to identify those elements right from the very beginning, of course. So let's replace r with 10. We'll have half times pi times 10 squared. 10 squared is 100, and half of 100 is 50. So for the area of the half circle, which I'm going to highlight here in yellow, we end up getting 50 pi, then rounded to the nearest tenth, that's about 157.1 meters squared. Now you'll notice in my work I'm putting the labels on the in-between steps. You can wait until the very end to put the label on, but you'll notice that in my work. So the area of this entire yellow shaded region is about 157.1 meters squared. Now I have some triangles next. I'm going to call these both region 2 together. They're both the same size, so that makes life easy. We can find the area of one and then just double it. So the formula for the area of a triangle is half times base times height. The base and height need to intersect at a 90-degree angle, and that's kind of implied right around here where my cursor is. So where the semicircle and the triangles meet, that would be a right angle, and then the base of the triangle would be 10 and the height would be 8. So the base and height are 10 and 8. That's the same as the radius of the half circle. Half of 80 then is going to get us 40. I did double it, as you can see, since each of those would be 40. Sometimes students like to write like the areas inside the figures, so 157.1. This triangle would be 40 meters squared. This triangle would be 40 meters squared. I did just double it to end up getting 80 meters squared for the two triangles together. And again, that's for this entire green shaded region, which I'll highlight as best as I can here. Now to find our total area, what we're going to do is we are going to add those areas together. So we're going to add the 80 from the two triangles plus the 157.1 from the semicircle to get about 237.1 meters squared. All right, next let's take a look at this really complicated shape here. We've got some semicircles, we've got a rectangle, we've got a triangle. I'm going to split this up right along here, and I'm going to draw a line, a vertical line going down to create a rectangle and then a triangle. So I'm actually going to start with the rectangle, which I'm going to call region 1 here. And I will highlight this one in yellow for us. So I'll outline this. Our base and height of this triangle, or length and width of the triangle, will be 9 and 6. So to find the area of this, if I said triangle, I'm sorry, our rectangle, the base and height, or the length and width of our rectangle will be 9 and 6. It's been a long week. So to do length times width for the area, we'll do 6 times 9, or 9 times 6, and that will get us 54 yards squared. So this entire region right here will be 54 yards squared. Let's move on next to the triangle. So that's going to be shaded in green here. I'll go ahead and highlight that for us. So we have to identify the base and height. This 5 yards could actually be shown inside the triangle from the tippy top over here on the right down to the base, which happens to be the right-hand side of this rectangle. So that's going to be the height, which means the base is going to be this side of the rectangle, which is 6. That's actually this 6 over here. The 6 yards, I know it's kind of confusing that's here, is the diameter of this half circle. So we would do half times base times height. The base would be 6 and the height would be 5. That gets us an area of 15 yards squared. We're going to have half of 30, which is going to get us 15 yards squared. And again, that's for the green triangle that we have. And we can do these in any order. The next one that I did was the larger semicircle. I'm going to call that, I call that region 3. Got to label those. And I'll highlight this guy in blue. So it's going to be this. And we need the radius of this half circle. Our formula is going to be half times pi r squared. So the diameter, which goes the whole way across, is 9 yards, the same as this dimension up here at the top of the rectangle. Half of 9 is 4.5. So the radius would be 4.5. So we'll do half times pi times 4.5 squared. 4.5 squared gets us 20.25. Half of 20.25 is 10.125 pi. Now we usually do round that to the nearest tenth, so that's about 31.8 yards squared. Again, that's for region 3, which is the larger semicircle. And then finally we're going to have the smaller semicircle, which I'm going to call region 4, and I'll highlight this one in that pinkish purplish color. Now the diameter of this semicircle, I already said it, and it's kind of hard to see now that I highlighted here, but that is this 6 yards. It's kind of like where that black wiggly line is. So our diameter is going to be 6 yards, and that means our radius is half of that, so that would be 3. So we'll do half pi r squared, which will be half times pi times 3 squared. Half of 9 is 4.5, so it will be 4.5 pi, which is approximately 14.1 yards squared, and that's for our smaller semicircle. To find our total area, we just need to add all those guys together. So we've got to add the 15 from the triangle, the 14.1 from the smaller semicircle, the 31.8 from the larger semicircle, and the 54 from our rectangle. And that will get us approximately 114.9 yards squared. Continuing with numbers 15 and 16, we're going to find the area of some more composite figures. So for question number 15, we'll notice that we have a rectangle and 2 semicircles on either side. And those 2 semicircles are the same size, and if we put them together, it'll form one whole circle. So we're going to go ahead and start by finding the area of the rectangle. I'll call that region 1, and I'll highlight that in yellow. So that's going to be this space right here. It has dimensions 16 inches by 11 inches. That's going to be our length and our width. And the area of a rectangle we know is either length times width or base times height. So we'll take 16 times 11. That will get us 176 inches squared for region 1. We then have the 2 semicircles, which are both the same size. We want to notice first that the diameter of each of these semicircles is 11. That's the distance the whole way across the circle. The radius then is going to be half of that, which means it's going to be 5.5 inches. So if we find the area of the semicircle, we'll do half pi r squared, replacing r with 5.5. So we have half times pi times 5.5 squared. 5.5 squared is 30.25. Half of 30.25 is 15.125. So if we want to write our answer in terms of pi, we'll have 15.125 pi, which is about 47.5. And again, that's for each of our semicircles, which I'll highlight here in green for us since I didn't already do that. And they form one whole circle. So I do want to point out that another option for how you could do this is just treat it as one whole circle and do pi r squared using 5.5 as your radius. You'll notice that I did semicircle formula here, multiplied it by 2 to get the area of both semicircles together, which is a whole circle. So if we remember, for our rectangle, we had an area of 176 inches squared. For our two semicircles together, we had an area of 95 inches squared. And again, we could treat those separately as 47.5 for each of them, and then just add 47.5 to 47.5. So when I go to find my total area for this region, it kind of looks like a track. We'll do 176 plus the 95 that we get from the two semicircles, and our total area is 271 inches squared. For our next example, we have another one of those sideways ice cream cones where we have a semicircle or half circle, and we have a triangle. So looks like we found the semicircle first. We'll call that region 1. And we'll highlight this in yellow. And just a reminder, the formula for the area of a semicircle or half circle is half pi r squared. Let me move this 1 out of the way if I can. Ooh. There we go. Get that out of the way. Our diameter of this semicircle is 10, which means the radius has to be half of that, or 5. Remember, it is only a half circle, so we'll do half pi r squared using that formula on the formula sheet. We'll do half times pi times 5 squared. 5 squared, of course, is 25, and half of 25 is 12.5 pi. So if we want to write our answer in terms of pi as an exact answer, we can write it as 12.5 pi. The decimal, though, makes a whole lot more sense for us for this situation. That's about 39.3 centimeters squared. And again, that's for the semicircle or region 1. We also have our triangle, which we're going to call region 2. Sometimes students want to split that into two triangles because of the dotted line. Just treat it as one big rectangle that I'll highlight here in green. Not rectangle, triangle. Treat it as one big triangle here. I'm going to go ahead and shade it in green for us. The base and height of this triangle will be 10 and 15. We can see that they meet at a 90-degree angle here. So the base is 10, height is 15. So for the area of a triangle, we'll use the formula half times base times height. We'll replace b with 10 and h with 15. Half times 10 times 15 will get us a total area of 75 centimeters squared. When we go to find our total area for this region, again, our sideways ice cream cone we have, we'll add the 75 we got from the triangle to the 39.3 that we got from the semicircle, and our total area is about 114.3 centimeters squared. All right, let's move ahead to questions 17 and 18 as well. Don't forget, you can try some of these questions on your own. These last two questions before we get to our final composite shape are very similar, except one has two triangles, the other shape only has one triangle. So in number 17, we obviously have a rectangle with a triangle above, and again, you don't need to split that triangle into two separate triangles, just treat it as one big triangle. So we're going to start with the rectangle. We'll call that region 1. I'll highlight that in yellow. So go ahead and outline that here. Our dimensions, we're going to use length times width or base times height for the area of the rectangle. Our dimensions are 10 by 5. So we'll do 10 times 5 to get the area of region 1, which I'll label here for us. That's going to get us an area of 50 centimeters squared. And again, that's for region 1. Region 2 is going to be our triangle. Go ahead and label it off to the side here. And I'm going to outline this one and highlight it or shade it in green. The height of this triangle is 3 centimeters. The base is the same as one of the sides of our rectangle, which is 10 centimeters. The formula for the area of a triangle is half times base times height. So we'll do half times 10 times 3, and that will get us an area of the triangle of 15 centimeters squared. Now we find our total area of both regions together. We'll move these boxes out of the way. We'll take the 50 from our rectangle plus the 15 from the triangle, and that will get us 65 centimeters squared, so a pretty standard question. All right, let's talk a little bit about our last question from this section. We will see one in just a few moments. It's a little bit more challenging, and it's pretty similar to the one that you'll see on our unit assessment. So in number 18, we have a rectangle in the center. We're actually going to start with that rectangle. And then we have two triangles. They are congruent, meaning they are the same size. So let me go ahead and highlight this rectangle in yellow. We're going to call this region 1. The dimensions of this rectangle are 24 and 8. So we'll do 24 times 8 to get the area. That will get us an area of 192 yards squared. Region 2, that's going to be our two triangles, and I'm going to treat them together instead of doing it really separately here. So we'll find the area of 1 and then double it. Sometimes students notice, and I should have mentioned this before, that when we have like the area formula for a triangle and we have two that are the same size, you could essentially take the 1/2 out of the formula and just do base times height, or even the two semicircles, if they're the same size and it can form one circle, you could just do pi r squared. That could work as well. So I'm going to highlight these regions in green. Go ahead and highlight that right there. And this region as well. The formula for the area of a triangle is half times base times height. And again, both those triangles are the same size. So we'll do half times 24 times 8. The base of each of these will be 24, the longer side of the rectangle. The height will be 8. So that will get us an area of 96 for each triangle. But we want to double that since we have two triangles of the same size. So for the two triangles combined, we'll also get an area of 192 yards squared. So what we'll do from here is, we'll get all these gray boxes in the way apparently. What we'll do from here is we'll add the 192 that we got from the two triangles to the 192 that we got from the rectangle to get a total area. Whoops, I want that to be yellow, my fault. Erase that and highlight it in yellow. That'll be better for us. There we go. So the 192 from the rectangle to the 192 we have from the two triangles, and we'll get 384 yards squared for the total area. Now again, there's a lot of examples here. I do hope that you tried at least some of these on your own. That way you could get some experience practicing finding area of composite figures. Know that there's a lot of steps involved here, so it's really easy to make some mistakes. So if you do, expect that you might make some mistakes on these problems, as there are quite a few steps, which means quite a few spaces or spots where we can make mistakes. So this next question is going to be really similar to a question you're going to see on the unit test. So we have this composite shape, and there's lots of ways we can break this apart. So I'm going to break it apart in one way, but there are definitely other ways to break this apart in order to find the area of the region. So the way I'm going to split it is, and I'm going to change the color of this line so it's a little bit easier to see, is I'm going to draw a vertical line right here, and we're going to separate this into 3 regions. Now this could actually be just 2 regions, a rectangle, and then this whole thing would be a trapezoid. I've seen students draw a horizontal line here instead of a vertical line. I've also seen students, and this is a really creative way to do it, draw a diagonal line from this corner here down to this corner, and that actually creates 2 trapezoids. So that is one way to approach it. But this is the way I'm going to do it just for the purposes of this video. So we're actually going to start with the rectangle that's on the left. I'm going to name that region 1, and I'm going to highlight that in yellow for us just so we can easily see it. So that's going to be this region here. The dimensions of this rectangle are 9 by 4. It's 9 feet high and 4 feet wide. So to find the area of that region, we're going to do length times width and take 4 times 9. So the area of that yellow highlighted region will be 36 feet squared. Region 2 is going to be this rectangle that's in the center, and I'm going to highlight this in green. It is 9 feet across, but then we need to find the height of this rectangle. So if we know that this entire length here is 9, we know this entire length here is 9. I know this part that's on the yellow rectangle is 4, which leaves 5 feet for this space right here. So I'm going to go ahead and label that with a 5. We'll make that a little bit smaller. So what I know here is that the height of this rectangle is going to be 5 feet. So I'm going to do length times width, which is 5 times 9. That will get me an area of 45 feet squared, and that's for this green highlighted rectangle. Now region 3 is going to be this tiny little triangle here, and make that 3 a little bit smaller. I'm going to go ahead and highlight this in blue. We need to identify the base and height of this triangle. So the height we actually already know is 5 because it's going to be the same as the height of this rectangle. I'll just slide that 5 over there. So the height is 5. I know that the yellow shaded region, the green shaded region, and the blue shaded region all together are 16. I know that this portion right here is 4, the yellow portion. I know that the green portion is 9. And that totals 13. So in order for the whole distance across, including yellow, green, and blue, to be 16, it means that this base has to be 3 here. So the base and height of the triangle are 3 and 5. Now you might be thinking, what about this 5.8? We don't actually need it for the area because it's not the base or height of the triangle or the rectangle, either of the rectangles that we have. We don't actually need that dimension. So we'll do half times 3 times 5, which gets us, sorry, that was a poor move on my part there, half of 15, which is 7.5 feet squared. Again, that's for the blue highlighted region. And to find our total area, we need to add all those together. When we combine the 36 feet from the rectangle on the left to the 45 from the rectangle in the middle to the 7.5 from the triangle, our total area is 88.5 feet squared. Even if you approach this in a different way, you should get the same total area. Your in-between steps might just look a little bit different. Now we're talking about the perimeter of the figure. That's what it asks us to do in question number 20. That's the distance around the outside. We should not split this into separate regions because all we're trying to do, and I'm going to go ahead and highlight this in purple, is find the total distance around the outside of this shape. So I'm going to add all of these dimensions up that I'm highlighting in purple, and this is where we need the 5.8. So we'll go ahead and add all those up. I did 4 plus 4 plus 9 plus 5.8 plus 16 plus 9 to get a total perimeter of 47.8 feet. Okay, so we're going to get into some somewhat application types of problems related to composite shapes. Question number 21 asks us, or tells us, that the Andersons are going to refinish their back porch, and it gives you a figure that looks like this. I added a line in there. I'll move that out of the way. But it gives us a shape that looks like this, which is pretty typical. I mean, often we have porches, we have decks, we have pools, lots of different architecture that may not be just a square or a rectangle or a perfect circle or something like that. So our first part of this is to find the area of the porch. So there's a couple of different ways to split it up, but I feel like the easiest way to split this up is to move this line, or to create this line that's a vertical line, and it creates a square and a trapezoid. So it creates two different regions for us. So I'm going to start by finding the area of the square, and it's an 8 by 8 square, so that's right here. And I'll do s squared, which is 8 squared, so the area of the square will be 64 feet squared. So that's for this region right here. I'll just go ahead and type in a 64 here for the area of the square. The other shape is a trapezoid. Now, some students might want to split it up into a rectangle and a triangle. I think the easiest way to do this is to just do the area formula for a trapezoid, which is half times the height, b sub 1 plus b sub 2. So the height of this trapezoid is the distance between your two parallel sides. I'll highlight that height in green. That's going to be this 7-foot length here. And then in yellow, I'll highlight the two parallel sides, which will be this side right here and this side right here. So our two bases will be 19, and then the 7 plus the 8 from the square, so that'll be 15. So to find the area of the trapezoid, I'll do half times 7, the height of the trapezoid, and then in parentheses, 15 plus 19. So the area of the trapezoid ends up getting us 119 feet squared. So for the total area, whoops, sorry, I had the trapezoid name hidden underneath that box. The total area will be 64 plus 119, which is 183 square feet. Part B says each gallon of wood stain will cover about 300 square feet. If the Andersons want to put 2 coats of stain on the deck, how many gallons of wood stain will be needed? Well, if the area is 183 square feet, and we're going to cover that twice, that means we need to cover 366 square feet. If we need to cover 366 square feet, that's more than the 300 that it covers. So we're going to need 2 gallons to cover this deck. All right, part C. It says each gallon of wood stain costs $37.98. How much will it cost to stain the deck? Well, we need 2 gallons, so 2 times $37.98. We'll get us $75.96. Again, a pretty realistic, real-world kind of problem, determining how much paint you need, how much stain you need, or something similar to that if you're painting a room or you're staining a deck, or you're going to maybe fertilize a lawn would be another good example of when you would need to come up with an estimate for how much you might need to purchase using the area. Let's go ahead and take a look at our next question. Number 22, it says a blueprint of a playground for a local community consists of a rectangle and 2 semicircles as shown in the diagram below. The scale is 1 inch equals 12.5 yards. Keep in mind that since the scale started with 1 inch equals 12.5 yards, we can easily convert each measurement to yards by simply multiplying by 12.5. But if the scale did not start with 1, we could do the conversions using a proportion each time. Or as we'll see in a later example, we can convert it to a 1 inch scale to make it a little bit easier for us. So in part A, it says to find the area of the actual playground to the nearest tenth. So obviously this is a model or drawing where the dimensions are in inches. We want to convert those dimensions to yards. So I want you to keep in mind that even though 1 inch equals 12.5 yards according to the scale, that does not mean that 1 square inch represents 12.5 square yards. So it is easiest to first convert each measurement to yards before finding the area. So you'll notice that I did that here. I took the 1.2 times 12.5 to get 15 yards. That's for this 1.2 inches. And then 2 times 12.5 to get 25 yards. And I'm actually going to type that into the picture here. So I'll just type underneath here that this is 25 yards. And up here, I'll type that this is 15 yards. I'll slide that over so it's a little bit easier to see. So we have our rectangle. I'm going to go ahead and start by finding the area of the rectangle here. I'm just going to go ahead and delete this box that's covering that work. That's going to be length times width. And I'll slide back up, so I'm going to go back and forth a little bit. Length times width will be 15 times 25. The area of that rectangle is 375 yards squared. Now we have 2 semicircles, but they're the same size, and if we imagine taking out that rectangle and putting those 2 semicircles together, that would form 1 circle. So you can treat it as 1 whole circle. I'll go ahead and delete this work here. The diameter of the circle is 15 yards. That's the whole distance across. So the radius will be half of that, which will be 7.5 yards. I just use the formula pi r squared and use 7.5 as our radius. So I took pi times 7.5 squared to get 56.25 pi. That's about 176.7 square yards. That's for the 2 semicircles together. So then what we want to do is we want to find the total area. the total area we will get by adding the 375 plus the approximately 176.7 square yards, which is the 56.25 pi. And that's going to get us about 551.7 square yards for our total area. Part B is an interesting question because it involves circumference. So it says the local community wants to enclose the park with fence. And that is an example of where we would use perimeter, or circumference in this case. Well, circumference and perimeter, I guess we would combine both of those. So we want to write an expression in terms of pi to represent the amount of fence in yards needed to enclose the park to the nearest tenth. So it says to the nearest tenth, but it also asks us to write our answer in terms of pi. So we'll put the answer in terms of pi, and then we can always calculate that as well. So the first thing we want to consider is what parts of the composite shape will actually be enclosed by the fence. So if we're looking at the outer edges here, I'm going to go ahead and slide back up. That's just going to be these outer edges. I'll highlight them the best that I can in yellow. So that's going to be the two sides of the rectangle, the two longer sides of the rectangle. And then the circumference of each of these semicircles. So if we put the two semicircles together, it's one whole circle. So essentially we're finding the circumference of a circle and then adding on the two longer sides, which will be the 25 yards. So we'll go ahead and slide down and we'll do that work. So we'll start with, go ahead and delete this box, the circle. The circumference is 2 pi r, so that's 2 times pi times 7.5, which is 15 pi. Again, that's for the two semicircles together. So to find our total, we want to take our 15 pi from the circle, plus the 25, plus the 25. If we write our answer in terms of pi, which it asked us to do sort of, it was a little unclear, we would write 15 pi plus 50 yards, or 50 plus 15 pi yards. Now calculating that, I'm going to go ahead and grab my calculator here. That would be about, and I'm using just my cell phone because that's what I have handy right now. Looks like that would be about 97.1 yards, if I did that correctly. So I took 15 times 3.14 for pi. That got me 47.1, and then I added on the two longer sides of the rectangle, 50 yards, to get about 97.1 yards. So if we wanted to round that to the nearest tenth, we could do that as well, which is what we would do typically in real life. All right, so our next example is modified from Glencoe's Advanced Math or Pre-Algebra textbook from question number 5 on page 570, but it's a similar type of question to our last couple. So it says that Hassan has designed a scale drawing of a brick walkway as seen below. The scale of the drawing is a 1/2 inch equals 4 feet. We want to find the area of the actual walkway. So what I did was I actually took my scale, since it wasn't in terms of 1 inch, and I just doubled 1/2 inch to get 1 inch, doubled 4 feet to get 8 feet. And then I was able to easily convert each of these measurements. Since 1 inch represents 8 feet, we also have 1/2 inch represents 4 feet. This dimension right here is 4 feet. The 0.75 inches will be 6 feet. I can get that by taking 0.75 times 8. The 1/2 inch down here, again, is going to be 4 feet. And then the 1.5 inches, if I take 1.5 times 8, that's going to get me 12 feet. So the way I broke this down, I'm going to go ahead and delete this section here, was into a rectangle and then I believe a trapezoid. So let's look at the rectangle up here. We're going to do length times width, so that's 4 times 6. Again, I like to convert my measurements first so that I don't have to convert at the end. One, because I will sometimes forget to convert at the end, or make sure we're not multiplying by 8, but since 1 inch represents 8 feet, 1 square inch actually represents 64 square feet. So you have to remember that fact as well. So the area of the rectangle is 24 feet squared. Let's do the trapezoid. So it's 1/2 times the height. The height of the trapezoid is this 1/2 inch, which is 4 feet. And then my parallel sides will be this 4 feet right here and the 12 feet down at the bottom. So we have 1/2 times 4 and then in parentheses 4 plus 12. That's 1/2 times 4 times 16, which gets us 32 feet squared. So our total area will end up being 56 feet squared. So we've got 24 plus 32 to get 56 feet squared. For part B, it says one case of bricks costs $25 and covers 6 square feet. How many cases are needed to cover the walkway with bricks? And then what would be the cost? Well, we have 56 square feet to cover. If we take 56 divided by 6, since every case covers 6 square feet, that gets us 9.3 repeating. We can't buy 0.3 repeating cases, so we're going to have to buy 10 cases. So to find the total cost, take 10 times 25 to get $250. All right, we're going to wind up these guided notes by looking at the area of the shaded region. So in number 24, what we're trying to do is find the area of the regions that are shaded. Now, often I'll have students say, oh, well, these are semicircles, right? So can I find the area of these semicircles? They're not quite. Imagine if you put 2 of these together, it wouldn't really form a circle. It would form more of an oval. So instead, what we want to do for something like this is find the area of the whole circle and then take away the part that's not shaded, which in this case is the square. So in order to find our solution, our area of the shaded region, we're going to find the area of the circle and subtract the area of the square. I'm actually just going to delete all this because we'll look through our work. We'll show you where we came up with these in a moment. So for the area of the circle, that's going to be pi r squared. And the radius is shown right here to be 8 inches. So we're going to do pi times 8 squared. Go ahead and slide this down. That's going to get us 64 pi. I kept it as that. You can also write it as 201.1, but the area of the circle is 64 pi. So you can see, and I'll highlight this in yellow, that I took this area for the area of the circle and I just plugged it in right up here. And I want to take away the part that's not shaded, so that's the square. So the area of the square is s squared, which is every side is 11.3 inches. So that would be 11.3 squared. 11.3 squared is about 127.69 square inches. So you can see that I plugged that in here for the area of the square. So to find the area of only the shaded region, I'm going to take that 64 pi, or about 201.1 square inches, subtract off the 127.69 for the area of the square, and that's going to get us about 73.4 square inches. So number 25, if I want to find the area of the shaded region, I could treat these as 2 separate triangles. The problem is I'm not exactly sure where this point of this right triangle is. So I know that this whole distance is 13 feet, but I don't really know how far this pointed part, or this top of the triangle, this peak of the triangle is. So what I would do is find the area of the trapezoid and then subtract off the non-shaded part, which is the triangle. So let's go ahead and start with the area of the trapezoid. That's going to be half times the height, and then b sub 1 plus b sub 2. So the height of the trapezoid is 11 feet. The parallel sides will be 13 feet and 16 feet, or 6 feet. So you can see that I plugged that in. We have half times 11 times 6 plus 13 in parentheses. That's going to get us about 104, well, exactly, I shouldn't say about. It's going to get us exactly 104.5 feet squared. And again, that's for the area of the trapezoid. So you can see that I plugged that in here. We'll find the area of the triangle next, and we'll subtract that off since that's not shaded. So that's going to be half times base times height. The base and height of the triangle meet at a 90-degree angle. Those are 11 and 6. Half times 6 times 11 gets us 33 feet squared for the area of the triangle. So you can see that that is 33 feet squared, and I plug that in there. In order to find the area of only the shaded region, take the area of the trapezoid, and we will subtract off the area of the triangle to get 71.5 feet squared. All right, our last example, number 26, is kind of interesting because there's more than one way to approach this problem. So one of the ways that we can do this is kind of like we did the last few problems, which is we take the area of the large triangle, which is the whole shape, and then subtract the area of the smaller triangle, which is this one right here, to find the area of the shaded region. So let's start with the area of the larger triangle. That's going to be half times base times height, so that's half times 16 times 12. which gets us an area of 96 meters squared. Now again, that's for the area of the larger triangle, which I'm going to go ahead and outline here in yellow. So that's going to be this entire triangle here. And you can see, again, the area of the larger triangle happens to be 96. There we go. We'll subtract off the area of the smaller triangle. I'm going to highlight that one in green. So that's this one right here, the thing that's not shaded. And the base and height of that triangle are 10 and 7.5. So I'm going to do half times 10 times 7.5 to get the area of the smaller triangle, which is 37.5 meters squared. So to find the area of only the shaded region, we're going to take 96 minus 37.5, and that gets us 58.5 meters squared. But what you might also notice is that the shaded region happens to be a shape that we know. The shaded region happens to be a trapezoid. So we could actually just use one formula, which is the area of a trapezoid formula. What we need to recognize here, and I'm going to go ahead and erase some of my highlighting that I've already made here, but we have to know what the lengths of the parallel sides are and what the height of this trapezoid will be, and that's where some students struggle a little bit. So for this, we're looking at this region here, and the lengths of the parallel sides are 12 and 7.5, so you can see that I plugged them in here. And the height of the trapezoid is 6. That's the distance between the two parallel sides, so that's this segment right here. Well, I know all of this is 16. The non-shaded part is 10. 16 minus 10 is going to get us 6. So we don't need the non-parallel side. We don't need the side that's at a diagonal here. It's not going to be the height of the trapezoid or either of the bases. So I don't need that, but I do need to recognize that this is 6 right here. So you can take half times 6 times, in parentheses, 7.5 plus 12, and that will also get us 58.5 meters squared. Method 2 is a little bit easier, but if you don't recognize that that's a trapezoid, or maybe you don't know how to find the height of the trapezoid, that might be a more challenging way to approach the problem. All right, so we've seen a lot in this lesson. Lots of formulas, but you'll have a formula sheet to use, some word problems, some application questions, and things like that. And then, of course, we finished off with that area of the shaded region, something that we'll continue to practice even throughout the remainder of the unit, but we'll, of course, be shifting gears to some three-dimensional figures as well. So we'll see two-dimensional figures here, but also get into some three-dimensional figures moving forward. Thanks for listening.